So what are the types of strain in these interactions? When we have hydrogens eclipsing each other, it's just torsional strain because hydrogens are so tiny, they really aren't going to have any steric strain. With a hydrogen eclipsed with a methyl, that's also mostly torsional strain. Now, when we have the methyl groups eclipsing each other, we get both torsional and steric strain. And then in the Gauss staggered, we get only steric strain. So the torsional strain is only in the eclipsed interactions, but the steric strain can be in both depending on what groups are eclipsed. And sometimes torsional strain is called eclipsing strain. Now I can show you how, if you had your model, you could actually rotate it and see the difference between the eclipsed and the staggered. So what this shows right here is the staggered. And then if I rotate it, now I have the eclipsed. And now I have the staggered. Rotate again, the eclipsed, staggered, eclipsed, staggered, eclipsed, staggered, eclipsed, staggered, and so forth. Now let's try an example. So we want to draw the Newman projections for 2-bromobutane looking down the C2-C3 bond. And you want to label each Newman projection as staggered, anti-staggered, gauche, or eclipsed. So I've started you off here with the Newman projection. So this is your starting point. And with this, notice that this is eclipsed. The methyls are eclipsing each other, and then the bromine and the hydrogen and the two hydrogens are eclipsing each other. So first of all, 2-bromobutane. So butane has 1, 2, 3, 4 carbons, and then bromine would be a carbon 2. Now if I'm looking down that C2 bond, if I wanted to draw this kind of like a sawhorse projection, I would have my H's here and my methyl up, and then this methyl would be up, and I'd have a bromine here and a hydrogen there. So this sawhorse projection corresponds to that Newman projection. So when you do this, you want to keep the front carbon still and just rotate the back carbon 60 degrees. So you can just keep the front carbon the same for all of these, and you're just going to change what's happening with the back carbon. Okay, so if I rotate this 60 degrees, then the methyl in blue will move over here 60 degrees. The methyl in red, it's on the front carbon, so it's just going to stay put in all of these. So I'm not moving the front carbon. And my hydrogens on the front carbon are also going to stay put, because I'm just rotating the back carbon. Okay, so the methyl in blue is going to move over 60 degrees, and then the bromine would also move over 60 degrees, and then the hydrogen would move over 60 degrees. So now that's the next conformer. Now let's rotate another 60 degrees. So when you're drawing the eclipsed conformers, I usually just draw the bonds a little bit to the side of the front bonds. They're right on top of each other, but visually you want to draw them just a little bit askew. So now the bromine will be here, the methyl in blue will be here, and your hydrogen will be up here. Now rotate again. Now we're going to go to a staggered conformer because we're always alternating between eclipsed and staggered. So now the methyl is going to be down here. The hydrogen will be over on the right, and the bromine will be up on the left. Now I rotate again to the eclipsed conformer. Now the bromine is here at the top. The methyl is over here, and the hydrogen is here. And then finally, I'm going to go back to one more staggered. And here the bromine will now be over on the right. The methyl will be on the left, and the hydrogen is here. So now we have all of the Newman projections drawn. So we want to label each as staggered, anti-staggered, Gauss, or eclipsed. So the eclipsed ones would be this, this, and this. And then the staggered would be this, this, and this. Now with the staggered anti versus staggered Gauss, the anti is the one which places the two biggest groups on the front and back carbon 180 degrees apart. So you may now be wondering, well, what's bigger, the methyl or the bromine? Because that makes a difference. Well, the size of the methyl group is going to be bigger than the size of the bromine group. So the anti will be the one in which the methyl groups are 180 degrees apart, which will be this conformer. And then these would be the gauche. Another question I could ask is, can you draw the Newman projections and then plot them on an energy diagram? I'm actually going to use a different molecule here. We're going to use 2,3-bromoethane. So let's first draw a Newman projection to start at 0, and I will, in questions, start you off with a particular projection. So let me start off with this one. So this would be the anti-projection. And so that's going to be the lowest energy conformer. Then if I rotate 60 degrees, I'm keeping the front carbon the same. Then my bromine goes over here, and my H is moved there. So now I have an eclipsed, so that's going to be higher in energy. So let's put that up here. And then if I rotate again, I'm going to get to a conformer where, again, the front carbon's the same, but now the bromine's over here. So now this is staggered, but it's gauche. So it's going to be a valley, but it's going to be a little bit higher energy than the anti. And then if I go to another 60-degree rotation, then I get to another eclipsed. But notice with this eclipsed that the bromines, the larger atoms, are eclipsing. So this is going to be actually a little bit higher in energy than the 60-degree eclipsed conformer. Then I rotate again, just the back carbon. I get back to a staggered. This is a staggered gauche, so it's going to be of equal energy as the one at 120. Then I rotate again, and I'm going to go back to an eclipsed. And this eclipsed is about the same as the eclipsed at 60 degrees. So energy level needs to be the same as the one at 60. So I'm going to kind of right on top of that there. And then 360, we would be back to what we started with. So we have our various energy levels. So now I'm just going to connect this with a curve. And this would be my anti-staggered. This is my gauche. And then this would be my eclipsed, all three eclipsed. But the one here is the highest in energy because it has the larger groups eclipsing. In summary, in Chapter 3, we learned about functional groups. We talked about alkanes being a class of saturated hydrocarbons, meaning they just have single carbon-carbon bonds. They're relatively unreactive. And constitutional isomers are compounds that have the same formula but different structures because their atoms are connected differently. Rotation's possible around sigma bonds, and therefore alkanes can exist in a large number of rapidly interconverting conformations. Newman projections are useful in visualizing the spatial arrangement of the atoms as a consequence of bond rotation, and the staggered conformers are more stable than the eclipsed conformers, and the staggered anti is the most stable, where that term is applicable.